everyone. We're going to kick off our second session in this room. It's IMDS, the Gatekeeper to your cloud castles, and how to keep the dragons out, by our speakers Liv Matan and Lior Zatlavi. Our sponsor for this session is NTT VC, and NTT VC is an independent venture firm formed in collaboration with NTT. Leveraging a unique strategy and deep industry network, NTT VC unlocks doors to relationships that can help founders and startups reach global scale. They also partner with first-time founders to launch startups. Over to you guys.
Hello, everyone. Thank you for joining our session. I'm Lior Zatlavi. I'm a senior cloud security architect for Hermetic.
And I'm Lior, a security researcher at the Hermetic research team. Nice to meet you guys.
Okay, and thank you for attending our session. So we're going to talk about a very important component of security in instances in the cloud called IMDS, or Instance Metadata Service. And the way this talk is going to go, we're first going to talk about this component across the different cloud providers, why it's so sensitive, and what protection mechanisms exist in the various providers for it. We're going to share from Liv's experience as a researcher as how one of these protection mechanisms actually foiled his ability to move forward with a vulnerability that he found. We're also going to talk about why you should still care, even though we have all these protection mechanisms in place. We're going to talk about how this corresponds with the shared responsibility model and what's your responsibility as a customer. So what is the IMDS? First of all, how many people here are aware of the IMDS? Right, great. How many people here think that they know it thoroughly, how it works? Okay, fewer hands, that's great. So the IMDS is basically a service meant for computing instances to serve credentials to applications running on them. So not every single application would have to manage their credentials separately. If that was the case, we would get a lot of access keys that exist for a very long time and slip away. We already get that today too, but hopefully we get less of it. So the way the mechanism actually works is that, for example, in AWS, if we have an EC2 instance, it would impersonate a proxy identity. In AWS's case, that would be an IAM role. It will then use a service to produce a credential. In AWS cases, STS, where it would produce a token. It would then store it on the IMDS, which will then be made available for applications via a query. Right? That's the basic. That's what we all know. And that query will serve it with the credentials, which will it then be able to use in order to access cloud resources. For example, it would be an S3 bucket or an RDS or whatever it wants to access. Right? Now, Azure and GCP have their own versions of this mechanism. They use OAuth tokens, but the basic idea is the same. And the reason why this talk is important, this mechanism is important, is that you can look at this query right here as sort of a wall. Right? In the previous conversation, they talked about, for example, how SSRF can actually be move you towards even remote code execution. And the reason for that is that if you are able to manipulate an application in order to exfiltrate these credentials, if you think about it, for all purposes relevant to accessing the AWS resources, you can essentially remote code execute, like literally remote code execute by having the credentials at your local machine, right? So for that reason, understanding how this wall is built and how it can be leveraged is a very, very important component. So with that in mind, let's go into the various mechanisms that there are. So in AWS, we actually have two versions, as I assume most people here know. There's V1, which was launched in 2009, and V2, which was introduced in 2019. And in Azure and GCP, they have their own two versions. So in V1, in AWS, we all know it's a painfully simple mechanism. It's a simple GET request into this local linked address where you have the role name, and then you get back to credentials. Now, it doesn't require you to manipulate headers when you make the request. You don't need to add your own headers to the request. You can just make a simple GET request, and it will also not block requests that have X44 header on them, as a lot of reverse proxies do, and that's how they're leveraged, that configuration, in order to extract credentials from machines used as reverse proxies. Now, Azure and GCP, in their own versions, also make a GET request. However, they require you to add an header, right? You need to include a header in the request in order to actually extract the tokens, and they will reject the X44 header in case it exists. Now, in V2 of AWS, which AWS again introduced in 2019, the handshake basically works in two steps. You first make a put request that retrieves back a token, which you then use in a GET request that you include that token as a header in that request. Now, that mechanism actually adds two very significant layers of security. The first one is that it requires you to perform two HTTP verbs, two kinds of HTTP verbs, a put and a get. And the second thing is that they actually had added a layer in the network layer, a security layer, that requires you, by default, unless you change it, to set a TTL, time to live, of 1 on the packet that is returned from the put request. So if you make a put request, by default, unless you change that configuration, that put request as the network packet that is returned as a response would have a TTL of 1. So that means that when it's routed back into the machine, that TTL decreases to 0, and supposedly it cannot be routed outside of the machine. Now, that makes this layer, this version, the V2, to have a very robust set of mechanisms, right? Of protection mechanisms. And you can see that as the overview of the various mechanisms that exist, right? So this is just an intro. And now Liv will share with us some of his experience trying to hack that.
Thank you, Lior. Can you hear me back? Good. So, Lior just reviewed the current IMDS security protections and mechanisms, and we're gonna showcase a case study we encountered during our research on the Azure's API management service. Now, we're not gonna go over onto the vulnerabilities, rather we're gonna highlight one of the vulnerabilities that was SSRF with the following capabilities: custom HTTP headers, method, and we had a clear response from the server. So, to those of you who are not familiar, SSRF is simply a vulnerability that allows attackers to force servers into sending unwanted requests to unwanted locations. With all of those capabilities in mind, it sounds like the correct and the ideal setup for IMDS credentials exfiltration, right? So, a brief on the vulnerability, we're gonna take a blitz on it. From the Azure portal, this is the feature that was vulnerable. These features allows the Azure's API management service users to retrieve external schemas from external resources. One of those resources was a URL the user can simply input. So the user inputs google.com, and behind the scenes, the course proxy of the service will send a request to google.com and retrieve the response to the user. So what we did is input our own hosted external redirect server that then redirected the course proxy that followed redirects automatically. That was the vulnerable aspect. Then with that, we had SSRF on the course proxy and we could access internal services. So then we said, we have the POC, we could access internal services, even the APIM Kudu server, to those of you who are familiar with it. And why not accessing IMDS, right? We will amplify the impact of the vulnerability, and it will be perfect for us. Can you guess what IMDS protection actually prevented us and denied us from accessing IMDS credentials? I will just tell you, it was the X-forwarded for header that was forwarded automatically and naturally by the course proxy. And with that forwarding, we tried to access the IMDS, and then the IMDS said, okay, I see the X-forwarded for, and as Lior just reviewed, I will deny this request. And with that, it shows the importance of this IMDS protection that the CSP that Azure introduced, and it reduced the impact of our vulnerability by far and drastically. But we will also showcase a case study that shows that even though the CSPs are constantly making efforts and investing efforts into making IMDS more secure, users can still misconfigure their environment and be vulnerable. So IMDS can still be abused for credentials exfiltration. So This case study, this scenario was on IMDS v2 in AWS, but it's also important to mention that it's applicable to all of the IMDSs that are currently available. So let's take an example. We encountered the Jira service of the victim, and as the script kiddies we are, we just input admin, and we logged into the portal, right? And we saw the version of the Jira instance, and with that, we also saw it's vulnerable to this CV discovered by asset node, and we saw the vulnerable Java code. The vulnerable Java code, simply, you see the path parameter here. This is our user input that is concatenated to the hard-coded Jira host, Jira-based URL. And we also have control over the method of the request and the headers of the request. Ideal setup, again. So the server expects a relative URL, but we, as attackers, obviously won't give it what it expects, and we will give it, for example, our first option is the @ that forces the server, the victim server, to treat the Jira host as credentials to the SSRF target URL that happens to be IMDS. The second option is to input .myevildomain.com that will have a DNS A record to IMDS, and with that, the server will treat the Jira host as a subdomain to our server. So we have the perfect setup. Why not trying abusing IMDS and exfiltrate credentials? And with that, we can specify the header, we can specify the put method that is required, get the token, send the token again, just as AWS IMDS v2 requires, and get the token. So we got the security credentials, we can now get RC on the workload, and that shows that no IMDS is bulletproof.
Thank you, Lee. So as Lee presented, no layer really can be considered as a silver bullet. And there is a lot of things that you can and should configure, both regarding the IMDS and also regarding security best practices in general, which we're not going to cover as part of this conversation, in order to secure yourself from the possibility or mitigate the risk of exfiltrating these credentials. And this is what we want to talk about today. Now, to simply put, when it comes to the shared responsibility model, the rule of thumb is whatever you can configure, you are responsible for configuring, right? And whatever the CSP has access to or controls or maintains, they're responsible for, right? I don't remember where I first heard it, but I really like this description. It's less of a shared responsibility model because you can't really share responsibility for the same thing. It's a split responsibility model, right? There are things that you control and there are things that the CSP controls. And you really need to understand what it is that you can configure. And we basically split this up into three lessons. The first one is avoiding bad defaults, because the devil really is in the defaults when we talk about this specific aspect. And I think the best example for this is AWS. So as we've shown before, this diagram sort of shows an AWS sandwich, right? So AWS has V1, which arguably has the least protection mechanisms, and V2, which arguably has the most protection mechanisms, the core of which are shown here, right? However, if you enable V1, right, which is, as we will see, very, very popular, if you enable V1 on machines, then having V2 was not going to help you because the V1 API will still be there. So you want to enforce V2. However, for a very long time, V1 was the only available version. So of course, for every machine that was configured before then and was not changed since then, it's still there. And on top of that, even when V2 was introduced since 2019, it was the default to have V1 enabled in all machines up until very recently. So it's just in their last October, this is the announcement, just in the recent October, it was made possible to configure an AMI in which the default will be to enforce V2, right? Up until then, any EC2 instance that was created, by default, V1 would have been enabled. So if you weren't conscious, or people in your organization weren't conscious of the IMDS or V1 in general, then they probably provisioned a lot of V1 enabled machines. And even since then, of course, a lot of AMIs out there still have V1 as the default enabled when you provision a machine. But of course, this is something important to know. So what we actually did was we sampled like several tens of thousands of machines from several environments, just again taking a sample. And we wanted to find out how popular IMDS V1 really is, right? Out there, we took like, again, a large sample, and 93%, over 93% of machines had V1 enabled on them. Now, the really interesting part was that over 55% of those machines did not show any kind of V1 calls, right? So they did not have any processes that were detected to actually use the V1 API, right? We mentioned this before because what you want to do in order to enforce V2 and to do it responsibly, you want to be able to make sure that nothing that actually needs V1 is actually running. And then when you find those, you want to retire them and basically upgrade them into better versions, right? That is the challenge, right? Just doing the enforcement is simple, but making sure that V1 is not really needed is very, very important. And to that aspect, we should give AWS some credit because they are incredibly serious about supporting their customers in this journey. And as we can see this as an example, they provide, for example, a metric in CloudWatch that lets you know where V1 calls were actually made. This is, by the way, how we were able to query the environments in order to see whether V1 calls were actually made in the past or not. Also in CloudTrail, if you look at events that were generated by EC2s, you can see a key that shows you in what version of the API, V1 or V2, the credentials were actually taken. So that is a great metric to show. And not 2 weeks ago, even, AWS released an open source that you can install on EC2 instances that tracks calls to IMDS V1 and V2 and creates a local log and then shows you not just that a call was made to V1, but also triggers and specifies the exact process that made the call. Right, so if you look at that log, you're not only going to be able to see that a call to V1 was made, you'll be able to know what process exactly used it, and then that will really help you with debugging it and go and replacing it with something that can use V2 in order to then eventually enforce V2. Now, when it comes to GCP, the default is actually a little bit, I would say, more serious because by default, EC2 instances, compute instances in GCP get very serious permissions. So in GCP, the way it works is you have a service account, it's attached to a compute instance, and whatever permissions that service account has, the compute instance can use unless it's otherwise limited. And by default, there's a default service account attached to computing instances. And that default service account, by default, has the editor role on it. Now, the editor role is a very, very powerful role, right? It can create, delete, manipulate most kinds of resources. For a lot of purposes, it can be seen as an admin role. And it's there, again, by default, unless you change it. Now, what you can do, and what is there, again, by default, is something as a mechanism, a legacy mechanism called access scoping, which scopes down the permissions that the compute instance can use. However, by default, it allows read-only access to storage. Now, an interesting part about access scopes is that GCP documentation actually recommends to use the general access scope, which basically means that it's not going to limit the permissions given on the machines. And what you should do is you should use the RBAC mechanism in order to provide least privilege, which is a good idea. However, what tends to happen a lot is that people simply remove the access scopes and leave the editor role there. right? So even the limitation that was there is now removed. And again, this is by default. What also happens, and not a lot of people are aware of, is that the editor role not just gets managerial permissions, right, control plane mechanisms, but also gets data access to storage. So to put it all up, to sum it all up, by the default mechanism, if you don't change it, this combination will give the compute instance read-only access to your storage, which is bad. It's really, really bad. And we sampled environments that we had access to, and about 18.6% of computing instances in GCP projects had this exact configuration. Now, we also reviewed how many people actually removed the scopes and basically allowed the editor role to be in full force, and that was also a lot. It was about 7.5% in the sample that we took. If that is an indication of what's going on there, that's pretty bad. So the first lesson is avoid bad default.
Thank you, Lior. So you guys remember this slide that Lior showed in the beginning of the presentation? So we have to confess we actually lied. In a research we did on those services in Azure, we found out they actually utilize a different IMDS or metadata protection that we haven't seen before in the other CSPs. And when we inspected those services, we saw that all of those services and potentially even more services in Azure share a similar runtime, perhaps even the same one. And with that in mind, they also share the same orchestrator and the same service to send the managed identity tokens that are attached to the workloads of those services. So if we use app service, for example, and we run code on it, and we try to make a CURL request just like in Azure Virtual Machines to get the managed identity token from IMDS, we will get bad access. But if we try to access it as follows, and for example, on Windows, we specify those environment variables as follows on Windows, we will get the access token and the managed identity token, just the managed identity token. And those environment variables are treated as kind of credentials, and this protection, if we look at it from the attacker's perspective, is actually very powerful, because now attackers, in order to exfiltrate credentials, will need to have RC, which is not that trivial on the workload, because they will need to have access to the environment variables, rather than just a simple SSRF with a header, with headers. And we also inspected the other services in the corresponding services in the other cloud providers, and we didn't see such mechanism, but in Elastic Beanstalk in AWS, we saw that IMDS v2 is enforced by default, so it's a good point. If we take it into a more practical insight of what we just showed you, and we set up a website on app service, and this website happened to be vulnerable to SSRF with a header capability. This website won't be vulnerable to IMDS credentials exfiltration. But if we set up the same setup and the same website on Azure Virtual Machines, it will be vulnerable to IMDS credentials exfiltration. So the moral of the story is don't send a VM to do a managed service work, and keep an eye of the purpose that you want to the purpose of your work and which services do you use. So a bit about compensating controls. We're not going to go over the generic security best practices because those are well known. Rather, we're going to go over some specific on each cloud provider in regards to IMDS credentials. So in AWS, you have this thing called data perimeter. To those of you who are not familiar, data perimeter is a set of preventive guardrails users can enforce in their AWS environment to make it more secure. Users should enforce. And AWS recently, a couple of months ago, introduced those new VPC endpoint condition keys specifically for IMDS credentials exfiltration that allows you to specify the source VPC and the VPC source IP and deny users were not using the credentials not from those conditions, from those VPC source IPs, after the credentials are already exfiltrated. Those condition keys can be enforced as CSPs or on an IAM role. In GCP, you have these disappearance of automatic runs of default service account. So as we said, default are dangerous. And with that, you can enforce an organization policy that will disable those automatic runs of service accounts, of the highly permissioned service account. Takeaways: IMDS is there whether you want it or not. So keep up with the CSP's evolvement. Make sure you know what you are configuring and what you are responsible for, because as we saw with the AWS IMDS v2 example, users can be mistaken and IMDS can be abused. Avoid bad defaults. Just like in the Azure example, use the correct services for the correct purpose and apply compensating controls. Some of those we just showed you. Thank you, guys.
Thank you, Liv and Lior. Any questions? Or actually, first question, who wants to ask the first? If you guys don't want to go, I'll go. So you talked about defaults, and you also talked about responsibilities. When it comes to those bad defaults, who's responsible for those?
So the customer is responsible for configuring the defaults, for configuring whatever the defaults allow them to configure, right? I'll put it this way. Just because a CSP made something the default doesn't make it its responsibility. Because as long as you have the responsibility, and this is why knowing is very important. This is why being conscious of these things is very important. As long as you have the ability to go and configure and avoiding that default, that is something that you need to do. Right, so even if V1, for example, as we mentioned, is the default in provisioning an EC2 instance, if you leave it configured and you don't make the effort of going and enforcing V2, that's of course your responsibility.
And so would you see that as a misconfiguration on the customer's end?
So it's widely considered today as a misconfiguration. In fact, you also you have many services, by the way, including our product, that indicates it as a misconfiguration, and also AWS config has a rule for it specifically.
Thank you.
I think I agree with you here, but at the same time, Amazon didn't offer IMDS v2 until 2019, which is also important to note that it was only one option, which was insecure. And if you look at like when Azure introduced the metadata header, they actually just turned it on for all customers, and then, well, maybe they broke some stuff in the ecosystem, but at least they did it in the right way there. If you look at the adoption today. But my question really is, with the packet analyzer, have you looked into using that to analyze more in depth, like whether you can detect opportunistic usage or exploitation attempts at IMDS, or to look whether people are actively trying to exploit SSRF? And does the packet analyzer have enough telemetry to do so?
So just to make sure I understand the question, you're asking about the open source that AWS released?
Yeah, if you looked into that yet.
Yeah, so we actually tried it out, and what it basically does, it's very simple, right? It's a process that you can load it up. It's open source, it's code. You can load it up as a process in the EC2 instance, make it run in the background, for example, and then when new requests are coming in. So let's say you make it run and then you test it out. You make a request to V1, you make a request to V2. It will log them. Right, and then what you need to do is what you can do. We can, by the way, I had a thought of actually building an open source around that for like multiple EC2s, because you still need to deploy it, you need to query it, you need to analyze the information. What you can then do is look at those logs and see which processes actually made the calls, and then that is a great enabler in going and finding those exact services. It's much better than just knowing that there was a call to V1 on the instance. That you can go and actually trigger and actually find a specific process is a great help.
All right, so thank you guys. We're going to wrap our session for right now. We'll be taking an extended break. Our next session will be at 10:40, so please enjoy Hallway Con, go speak to some vendors, go meet each other. Thank you. Thank you, guys.
Thank you, guys.